In this video, we're going to look at an example of reparameterizing a curve in terms of arc length. So we're given the vector valued function 2 over t squared plus 1 minus a 1 times I, and then a 2t over t squared plus 1j. We're asked to reparameterize this curve starting at the point 1, 0 and continuing in the direction of increasing t. Well, the first thing that we notice is that in order for us to start at the point 1, 0, we must have t equaling 0 as our starting point. We can see that pretty readily. To get a y-coordinate of 0 for my point, I need to plug in a 0 for t here in my second component. And then when I plug in a 0 for t into the first component, I get a 1 for the x-coordinate. So we have the t of 0 gives us our starting point. So to get us to reparameterize in terms of arc length into the direction of increasing t, we will integrate from 0 to t the magnitude of the derivative. We'll use a different variable here when we're integrating with respect to, because we don't want to use t in two different places, meaning two different things. So since I'm using my t here as what's being inputted in the upper limit of integration, I'll use a different letter here to integrate with respect to. So you should be able to check your derivatives here. The derivative of 2 over t squared plus 1 and then minus a 1 is negative 4u over u squared plus 1 squared if I replace the t with a u. And then in the second piece, you would use your quotient rule to take the derivative. This is what you would get using your quotient rule, substituting again a u for the t. And you can factor the numerator of that expression. Notice that you've got a 2u squared minus a 4u squared here. So you'll have a minus 2u squared. And then you'll have a 2 minus that. So you can factor a 2 out. When you square the 2, you get the 4. And you'll have a 1 minus u squared that you'll need to square as well. So in the next step, I've just multiplied out the numerator of the second fraction. In the following step, we've just put the two fractions together. We already have a common denominator. And we notice that we can refactor the numerator. We can factor out a 4. What's left factors as u squared plus 1 squared. Now we can cancel a couple of factors of u squared plus 1 in numerator and denominator. And then finally take the square root and see that we're integrating 2 over u squared plus 1. An antiderivative for that is 2 times inverse tangent of u. We're going to evaluate that from 0 to t. And since inverse tangent of 0 is 0, we just get 2 inverse tangent of t is what s will be. Now remember, we're trying to reparameterize this curve in terms of arc length, so I need to solve that equation for s and substitute. If we solve that equation for s, we'll get tangent, t is equal to tangent of s over 2. So if we start plugging some things in, we get tangent squared of s over 2 plus 1, and then minus a 1. Well, 1 plus tangent squared is secant squared. And then that secant squared would be in the denominator. Moving it up to the numerator, we rewrite the top, we rewrite that first piece as 2 cosine squared of s over 2. And then we have a minus 1 on the end. In the second piece, we do something similar. Tangent squared plus 1 is secant squared, so we get secant squared of s over 2, but we move it up to the top. We'll get cosine squared of s over 2. But there's a cosine in the denominator here. So after simplifying that, we'll get 2 times sine of s over 2 times cosine of s over 2. And then recognizing these as the double angle formulas for cosine and sine, respectively, I can rewrite the first component as cosine of s and the second component as sine of s. So reparameterizing this curve in terms of arc length, we get cosine of si plus sine of sj. And this tells us that we've actually got a curve, which is a circle of radius 1, centered at the origin.